Okay, so let's study about the chemical bonding and molecular structure. Let's continue to study about this in the detail. So, yeah, so ionic or electrovalent bond factors affecting the formation of ionic bonds. The formation of an ionic bond is related to cation and anions, which depends upon the following factors. First, low ionization energy of electropositive element. Second, high electron affinity of electronegative element. Third, high lattice enthalpy. So lattice enthalpy is directly proportional to the charge on ions upon size of ions. Note, elements of group 1 and group 2 on combining with halogens, oxygen and sulfur generally form ionic bonds, and bonding in compounds of transition metals in lower oxidation states is ionic with partial covalent character. Lattice enthalpy and its calculation. The lattice enthalpy of an ionic solid is defined as energy required to completely separate 1 mole of a solid ionic compound into the gaseous constituent ions. This energy is calculated by Born-Haber cycle. The Born-Haber cycle includes the vaporization of reactants into the gaseous state, conversion of gaseous atoms into ions, and combination of gaseous ions to form ionic lattice of the molecules. For example, here is just the metal in the solid state plus half of X2 in gaseous will give you Mx compound in the solid state. Delta H will be equal to Q, where del H is enthalpy change of the reaction and Q is the heat of the reaction. The above reaction includes various steps. It's not occurring in the single step. It follows the various steps. Like first, the metal in solid state convert to the gaseous states, and the energy or the heat it is taking is sublimation energy. Second, the gaseous metal will changes to the ion and lose an electron, and the energy which this reaction needs is ionization energy. Third, half of O2 in the half of X2 in gaseous state will form the X of uh, atom in a gaseous state, and the energy needed in this step is d by 2, that is dissociation energy. Next, this X of G or X in the gaseous state add an electron into them and become an ion, and the energy needed in this process is electron affinity. Then this ion which is formed from the metal and the ion which is formed from X combines together forming a compound in solid state, that is Mx, and the energy needed in this process is lattice enthalpy. So these are the steps occurring while this reaction is performing. Okay. Lattice enthalpy and its calculation. So overall enthalpy change of the reaction is given by del H will be del H1 plus del H2 plus del H3 plus del H4 plus del H5, or alternatively the equation can be written as del H is equals to the sum of all the energies which we needed to perform a single reaction. So S plus I plus D by 2 minus E minus U, in which U can be equal to S plus I plus D by 2 minus E minus del H. So note, a number of ionic solids are almost insoluble in water because hydration energy is smaller than their lattice energy. Examples of water insoluble salts are AgCl, AgBr, AgI, Ag2CrO4, PbSO4, BaSO4, and CaSCO3. So both lattice energy and hydration energy decrease with the increase in ionic size. If both anion and cation are of comparable size, the cationic radius will influence the lattice energy. Metallic bonding. So the attractive force which hold together the constituent particles in a metal is known as metallic bonding. The two models which explain metallic bonding are: first, according to the electron C model, metallic crystal consists of positive kernels packed together as closely as possible in a regular geometric pattern and immersed in a sea of mobile electrons. Second is, according to band model, the atomic orbitals of atom with same energy and same symmetry overlap to form energy bands. The highest occupied energy band is valence band, and lowest unoccupied energy band is conduction band. And the gap between these two bands is called energy gap. In insulators, energy gap is very large, while in semiconductor it is very small. And on increasing temperature, the electrical conductivity of semiconductors increases because some electrons move from the valence band to the conduction band. Molecular orbital theory. It is given by Hund and Millikan. This theory is a method for determining molecular structure in which electrons are not assigned to individual bonds between the atoms, but are treated as moving under the influence of nuclei in the whole molecule. Formation of molecular orbitals involve linear combination of atomic orbitals. Molecular orbitals formed are of two types, bonding and anti-bonding. So bonding molecular orbital are of lower energy and are represented as sigma or pi. These makes stronger bond. These makes bond strong. And anti-bonding molecular orbital are of higher energy and are represented as sigma star or pi star. These reduces the stability of the molecules. The electronic configuration of molecular orbital are written in the following manner. So for species like O2 and F2, this is the way through which we write the electronic configuration of the molecules. And for the species like Li2, Be2, B2, C2, N2, etc., this is the way or a manner or a proper process by which we write the electronic configuration of the molecules. Bond order for diatomic molecules or ions will be given by Nb minus Na upon 2, where Nb is the number of bonding electrons and Na is the number of anti-bonding electrons. The difference in this both and divided by 2. That comes out our bond order. The molecule is considered to be stable if Nb is greater than Na. That is, if bond order is positive, the molecule is unstable if Nb is less than Na or Nb equals to Na. That is, if bond order is negative or 0. Magnetic behavior of a molecule can also be conveyed from its electronic configuration. If any unpaired electron is present in electronic configuration, the molecule is paramagnetic, and in case of paired electrons, molecule is diamagnetic. So magnetic moment will be given by under root n plus 2 Bm, where Bm is Bohr magneton and n is the number of unpaired electrons present in the molecule. Resonance. There are certain molecules like benzene, ozone, nitric acid, and many more, whose all the properties cannot be explained by a single structure. Then, two or more structures called resonating structures are required to explain all the properties, and the actual structure is intermediate of these structure. For example, carbonate or ozone. So we have this here. We have here the diagram of ozone. So these are the two diagrams of resonance of ozone molecule, and this is the equivalent diagram for the ozone molecule. Resonance is shown by only those molecules which possess conjugate single and multiple bonds. It imparts stability to the molecule and hence decreases its reactivity. Since the electrons are not localized between any particular atoms and are uniformly distributed in the resonance hybrid, all the bonds are similar and are of equal bond length. Resonance averages the bond characteristic as a whole. The difference in the energy of a resonance hybrid and most stable structure is called resonance energy. Valence bond theory. It is given by Pauling and Millikan. It explains bond formation in terms of overlapping of orbitals. For example, the formation of hydrogen molecule from two hydrogen atoms involves the overlap of 1s orbital of two hydrogen atoms which are singly occupied. And because of orbital overlap, the electron density between the nuclei increases, which helps in bringing them close. The overlapping of orbitals may result in two types of bonds. First, sigma bond, and it is the result of end-to-end overlapping or axial overlapping between SS, PP, and SP orbitals. Single bond is always sigma bond. The electron density accumulates between the center of the atoms being bonded. So you can see this is the s orbital plus this is also s orbital, and this will give a SS overlapping, which is axial overlapping and forming a sigma bond. Here also you can see s orbital plus p orbital. This is giving a sp overlapping and forming a sigma bond. So valence bond theory, uh, pi bond, right? Second type of bond is pi bond. It is formed by the incomplete overlapping of orbitals, or in other words, sidewise or parallel overlapping of pp orbitals results in the pi bond formation. You can see that p orbital plus p orbital will give you pp overlapping. Double bond has one sigma bond and one pi bond, and triple bond has two pi bonds and one sigma bond. This is a point to remember. So VSEPR theory, and it was given by Gillespie and Nyholm. So VSEPR stands for valence shell electron pair repulsion. According to this theory, all valence shell electron pairs surrounding the central atom arrange themselves in such a manner so that they are as far away from each other as possible. So there are two types of electron pairs around the central atom: bonding electron pair and non-bonding electron pair. Non-bonding electron pair called lone pair. The strength of repulsion between the electron pairs varies as highest in lone pair, then lone pair, and then bond pair, bond pair. So hybrid orbitals and molecular shapes involving s, p, and d orbitals is given in this table here. So we have 4 columns. One is of number of electron pairs, second is of geometry, third is of hybridization, and then there are examples in the fourth column. So number of electron bonds. If we have 2 bond pair, then the geometry related to this number of electron pair will be linear, and the hybridization in this geometry will be sp, for example in BeF2. Second will be 3 bond pairs. The geometry will be trigonal planar, and the hybridization showing by this geometry is sp2. For example, BF3. BF3 has trigonal planar geometry and hybridization state showing sp2. Then 2 bond pair plus 1 lone pair. Number of electron pairs will be, and the geometry will be bent. Hybridization will be sp2, and examples are SO2 or O3. 4 bond pairs, geometry is tetrahedral, hybridization is sp3, and examples are CH4. And 3 bond pair plus 1 lone pair, geometry will be pyramidal, hybridization sp3, and example is ammonia molecule. Next number of electron pair is 2 bond pair plus 2 lone pair, geometry will be angular or V shape, hybridization will be sp3, and the examples will be H2O. Then the number of electron pair will be 5 bond pair, and the geometry associated with this is trigonal bipyramidal. Hybridization will be sp3d, and for example PF5 and PCl5, we can see this type of geometry and this type of hybridization. Next is 4 bond pair plus 1 lone pair. The geometry will be seesaw, and the hybridization associated with this geometry is sp3d, and examples are SF4. SF4 show sp3d hybridization and the seesaw geometry, and it has 4 bond pair plus 1 lone pair present in it. Next is 3 bond pair plus 2 lone pair. It is T-shaped and showing hybridization of sp3d, and examples are ClF3. Next is 6 bond pair showing geometry of octahedral, and hybridization is sp3d2, and examples are SF6. Next, 5 bond pair plus 1 lone pair, then square pyramidal is the geometry, sp3d2 is the hybridization, and example is BrF5. 4 bond pair plus 2 lone pair, square planar geometry, sp3d2 hybridization, and XEF for example. Last, 7 bond pair, pentagonal bipyramidal is the geometry associated with it, and sp3d3 is the hybridization showing by this type of geometry, and IF7 is the example showing the pentagonal bipyramidal geometry and the hybridization of sp3d3. So this is the table where the hybrid orbitals and the molecular shapes involving sp and d orbitals are given in the order. Okay, so we are at a summary slide. First point, the mixing of atomic orbitals to form new hybrid orbitals is hybridization. Dipole moment represented by mu is a measure of polarity of a bond. So mu is equals to q dot r. Fazan's rule, which we have studied, predicts the degree of covalent character in ionic bonds. Smaller cations and larger anions lead to more covalent character. Lattice enthalpy is the energy released when gaseous ions form an ionic solid. In resonance, molecules can be represented by two or more valid Lewis structures. These are the major points which we have studied today. Okay, thank you.